level, you do here the second, and here is the third level. But essentially, this is not considered to be the level. It's a matter of kind of, notation, but your remark is correct. Actually, we should be very careful with that sort of things. Then, because I have the feeling that you didn't really get it, I'll still struggle to explain it again. Should I? Yeah. No? Yes. Yeah. Okay, we can take a ballot. Who wants? Who is for? 1, 2, 3, 4? Should I assume that's a majority? Do you guys vote? I have also a bit of animation here. What is this animation saying? Then essentially, as I said, I split the operands in blocks of 4 bits. This is the first level of look ahead, even though it's not considered to be here look ahead. At each and every block, I can compute now the block generate and the block propagate for that block. I know the inputs, and generate and propagate depend on that. If you look at this implementation, what you see is that my block is computing P's and G's, but it's also computing some internal carries. But those internal carries, they also depend on the carrying into the block. Now, if I look at those 4-bit blocks, and I see 16 of them, even though only 4 are there, all the blocks except the first one do not know the carry into the block. The carries from each and 4 bit further. The first one is the lucky one. Then that one knows the carry, can compute the P and the G as everybody else, and can also compute the carry from position 0 to 1, from position 0 to 2, and from position 0 to 3. Those are valid carries, which I eventually can use if I want to. But the rest of the carries, even though the hardware is doing something, they have no good value. In order for them to have good value, I have to solve the next level of look ahead, which is I'm taking now bits, groups of 4 blocks. Each of these blocks is treated as a bit because it has a propagate and a generate. There are 4 bits inside, but I don't see them as bits. I just see the block. And I apply now the same trick at this level, and I can compute propagate and generate for the blocks. Now each block has 16 bits behind, but the structure is similar. P's and G's for the blocks. I can compute carries, and I can compute generate and propagate. Again, the least significant block is the lucky one, because the least significant block knows this carry, knows all these values, then it can compute C4, C8, C12. However, the next block is not that happy. The next block does not have this solved yet. And that's the reason why I have to apply again a look ahead. And now I'm combining 4 blocks of 16 bits with 1 look ahead. Again, now 16 bits are seen as a bit. And then with this last level of look ahead, I have everything solved. Because those are valid signals, and I know the carry in, which means carry 16, carry 32, and carry 48 are now solid, good values. It took me a traveling in a binary, in a quaternary tree from the lips to the root. I cannot go further because there is nothing to combine, and I don't have any kind of unknown stuff. What is happening now is that not only this 16-bit block is happy, everybody is happy. All of them do have the carry in. Because they have the carry in, all of these blocks can solve those carries. 4, 8, 12, 16, 20, 24. whatever. And this is now, you know, I'm coming back. I went to the root, and now I'm returning to the libs. When I have all those now ready, each 4-bit block can solve the carries inside the block. And then I have everything done. Now there is this animation which is saying, boom, 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 boom. Then I have everything, and now because I have everything, I can do it also in here, and I can do all the calculations. I don't like animations that much, but on the website of the book, you also have PowerPoint, and if you are animation fan, then you can do that. Is it a bit more clear? Now, if we take we don't take again a doubt. Then if it's not clear, you can always come and ask. Okay? I can hear also you. Then if you have some comments, do I hear you? No, you don't say anything, which is good, or not? Then, this is the principle of look ahead. Then the beauty of that is that I managed to solve a problem which was linear in complexity in a logarithmic time. Now, if I take 8 bits per block, the tree will have a log 8 depth. And it will be eventually faster in the sense that we'll have less levels. But each carry look-ahead block will be more complex. Then there is a trade-off between the number of bits that I can take in a block, the complexity of that, and the depth of the tree. And based on experience for the current technology, 4 bits seems to be the optimum. Now in here, you can compute, let's say, the latency of a 16-bit header. Then, now, you know, these discussions here are, in order to compute the P and a G, you say that you need 1 gate level. This is an approximation, because when you do AND and OR, you can think about 1 gate level. When you do XOR, it's slightly more complex, but from the theoretical point of view, it's 1 gate level. Then you compute P's and G's, and then you count here the levels, and in general, for a k-bit carry look ahead, this is the kind of complexity that you have. If you change the number of bits per block, those guys will change. Now, I'm very happy, but not quite. Now, I'm happy, I can tell you why I'm happy. Because I have a solution which is solving a problem in logarithmic time instead of linear time. But I'm not happy for other reasons. And I would like you to give me one reason why I'm not happy. Yes?
Area of the city?
No.
No.
No. No. As I said, area is commodity. I have full, you know, a lot of land, not like in the Netherlands. Your land is expensive. Hmm? What do you think I don't like? Mm. There is something which I fundamentally don't like. Yes?
You still have the propagation instead of the 4 bits?
Sorry?
You still have propagation in addition inside?
There is nothing that I can do to get rid of that. And there is no real propagation inside the block. It's look ahead going on there. This is based on binary representation, non-redundant. Then I have to pay a price in something, and I'm paying the price in area. And I said I don't care about area. Then you don't want to help me. There are 2 issues here. It's not really a regular structure. While the Ripple carrier, there was a nice rectangle with a beautiful kind of shape with the data flow, a clear data flow. This one will result in not such a nice layout. And most of the time what we want to have structures which are rectangular. Then somehow I have to pack this in a rectangular box, and this will change the length of the wires, and I'll have some problems. But that's not my main problem, my main reason for being unhappy.
We are constrained by the arithmetic number systems we can use because
We only use that in binary. We can use also other systems, it's very general. If I can represent numbers easier, then it's fine. There are a lot of transitions which do not really contribute to the calculation. I'm going down and I'm going up, and then carries, all the carries are floating up and down. Eventually they end up with the right value, but until then they are switching for no purpose. Glitches, what does they mean? Energy. Then I am consuming energy without really contributing to the calculation. And when that was invented, that was not very important. Today is very important. Then there are timing issues due to the layout and due to the fact that things are propagating back and forth. And there is an energy issue. Now, it was a Chinese guy, I think he was working for IBM, and his name was Ling. I think he's still alive. And he came with the idea to do carry look ahead, but to propagate Harry instead of carry. His name was Harry Ling. You know, most of the Chinese, they have a Chinese name and a European name, right? Okay. Then his European name was Harry. And what he said, you see, the look ahead is a clean concept. And I don't want to change it. What I want to do is to do this kind of calculation with less gates and try to simplify the implementation of the look ahead blocks, and somehow, because this is the, you know, the bottleneck of the calculation, to take some complexity from that carry network. And what he said, instead of propagating carry, as we do in look ahead, let us propagate a signal which he called Harry. You know, he was very modest. And he said, Harry, it's actually the war between carry into position I and carry into the previous position. It's still telling me a story about carry. And I'm not propagating carry, I am propagating the war of those carries. Now, if you do that and you play with some Boolean algebra, which I'm pretty sure you enjoy, what you obtain is a simpler implementation of the look-ahead stuff. Then, if you do, these are the, you know, the substitution, and this is the implementation of a carry look-ahead block, which now is propagating a Harry and not a carry. And those equations are simpler. Then you see, you save on gates, and you save on maximum gate fan-in, and you even save a lot more if you use what is called wired OR. That's a concept which is obsolete, but still we use it from time to time, which is instead of doing the OR by means of an OR gate, we do that by wiring. I will not go into that. The guys from microelectronics most likely know about that. They can deny, but I won't trust them. No, I trust you. If you deny, you know, you have to give people the benefit of the doubt. Then that's a technique which was utilized in early days in order to save gates. In that time, gates were expensive, and you could do an OR by just doing wiring, and you put a resistor, and it's called wired OR. And then this link technique was better from the point of view of the implementation. Now, the concept is the same. The only difference is what I'm propagating. But there is a problem. I mean, there is no way you diminish something and there is no pop-up effect in another place. You see, after I finish the propagation, I don't have the carries. I have the Harris for each position. I know the half sum for the bits, which is xi, xor, yi. I use that for propagate. But now I have to compute the final sum, which is based on what? This half sum and the carry, which is not a real carry. Then there is an extra complication in here, you see it. Then in normal carry look ahead, I just have to use an OR, an XOR. If I'm doing carry, I have to do a bit more complex calculation. Then this is the let's say, the advantage of link. It's based on an observation that a signal can be propagating. It is important that the information is the same, not what the way you do it. And then this was a beautiful kind of proposal. And then we'll go still towards logarithmic addition, but we'll try now to, let's say, to get rid of some of the carry look ahead problems. And this will bring us towards what we use today in adder design, which are prefix adders. They still do kind of carry look ahead. They are based also on propagate and generate, but they result in nicer networks, and they do not have back and forth traversals. They are the state-of-the-art solution today. It doesn't mean that carry look ahead is not important, and I will not ask you at the exam something about carry look ahead. Then don't say it's not important, we drop it, we don't understand it, because most likely I'll ask you something about it. Then, if I look at what we discussed thus far, we said I have 4 bits, I'm combining them in a block, and then I'm combining 4 blocks in another block, and so forth and so on. Now, let us look at this issue in a kind of different way. I think I would like to move to the PDF, because too much animation is not my style. May I do that? You may oppose. But you are not opposing, you are nice guys. Okay, now, I know that for 1 bit position, I can compute PNG. And I know that I can combine blocks of 4 bits and get PNG for the block. Now, let us concentrate now on combining only 2 of those. 2 blocks of 2 bits. And you see I have 2 blocks, block B and block B prime. They may overlap, as I told you before, because I'm focusing on carry, not on the calculation of sum. And I want to combine them in a larger block and compute PNG for that larger block. For that, I rely on what we call the carry operator, or the cent operator, because we use this notation, and this is a cent. Then, if I have PNGs for 2 blocks, the combination of them will be, together will propagate if both propagate, they will generate if G, okay, this cannot be correct here. This is a mistake. The most significant one is generating, or the least significant one is generating and the most significant one is propagating. And this is called the carry operator. And I can implement it in a very simple way. This is the way to implement it. Then when I see such a cent, I see that kind of gates. This is associative, but it's not commutative. Because I cannot do it the other way around here. Here I don't care because propagate applies for all of them. But the one which is in the most significant position is the one which counts first for generation. Then if I write this equation actually in the way it is here, it's wrong, right? Now, you know, I know you like mathematics, don't you? Yeah. I feel very confident. In mathematics, what we have is very often we want to compute prefix sums, which means I have some numbers, like here I have k numbers. And what I want to do, I want to compute the sum of them in an incremental way. Then, if I take, I am on x2, I want to know the sum of all the numbers before x2. Then, x2 plus x1 plus x0. If I am on the last one, I want to compute the sum of all of them. These are called prefixes, and they relate, you know, to the partial sums of those numbers. This is a well-known problem in mathematics, and there are solutions to solve it in an efficient way. Why? I mean, if I take it brute force approach, I can compute those in parallel, independent. But you see, when I'm computing x2, I actually rely on this partial sum. Then this can contribute here. Now, if I cascade them and I do it in a serial way, then when I'm computing xk minus 1, I'm relying on xk minus 2 sum plus xk minus 1. I have a serial stuff, and then its complexity is linear. I don't like it. Now, the idea will be to generate a kind of tree structure where you compute parts of those kind of independent, and then you combine them slowly until you get all of those. This is in arithmetic. And you rely on addition. Then my basic operation is addition. I take some of those numbers, I'm trying to combine them and to compute all the prefixes in a logarithmic time. Now I take the plus and I replace it with a carry. What I want in order to know or to solve the carry problem is to have all the carries in my network from least significant position towards the most significant position. Then carry 1, carry 2, carry k plus 1, whatever. Then there is a similarity within this, with those problems are very much similar. And what I would like to do is to use those propagate and generate in order to compute the prefixes, and use some of the techniques which are here in order not to do that in a linear way. This is the linear one. I start for the least significant position and I keep on combining those blocks, okay? based on this kind of cent operators. Assuming that those are bits, what I can do is I can take those, combine them. That's not good. This will give me linear time, and you know, in this case we don't like linear time. Now, this is a prefixed network, and this is about the calculation of prefix sums. Then my numbers are 6 minus 1, 2, 5. And what I want to make all the calculation of the sum. Then first it's x0, which is 5. I can report it for output. Then what I can do is I can continue the calculation in a slow way, or I can enable some parallelism. And I will say, at the first level, what I'll do, I'll combine pairwise numbers, and I compute partial sums of groups of 2. Then I add 2 plus 5, and 6 with minus 1. Now this will give me a final result for this column, and will give me some kind of intermediate result for most significant and the previous one. And also, I can rely on whatever I computed on the second column. Now, at this level, remember here I have to compute the sum of whatever is in this column plus all the rest. Previous stuff is already available, and with one enter I can get this. And in here I have to compute the sum of what's in here plus the rest. And plus the rest means what? I had already the calculation with my neighbor, and I have the previous value for the other two, and I'm done. Then what I see is that I got an approach which allowed me to share the calculations, then to utilize some of the calculations. I'm not looking directly to the computation, and now in the delay of two headers, I compute everything, delay-wise. I'm not talking about how many headers I'm using. Because if I want to do it serially, I can use only one header. But remember, I said I'm rich, I have a lot of land. Now, I can play the same trick now with bits. Then this is my least significant bit, and I want to compute all the carries. Carries from here, here, from here, here, and from here, here. Then, from the first position to the second position is trivial. It's 1 cent operator. In the same time, I'm looking in the future, and I'm saying, I'm combining those two. And I have carry from here to here. Now, based on the fact that I have the carry from here to here, and I have this position, I can combine them directly, and I get carry from 0 to 3. And because I have this carry, and I also have the carry from this to this, I combine those two blocks, and I have the... it's very boring, right? Hmm? Or it's too simple? Too simple. Always things which are simple. Okay. That's the principle behind the prefix headers. Now, the technique which I'm using in order to do that kind of smart combinations might be different, and we have different kind of headers. We call them Brain-Kung, Cogging-Stone, and there are many others. Now, they are based on a sort of divide-Integral approach. It was proposed by Lander Fisher. You know, people which did work in algorithms and things like that in the early days, when we were plus or minus ignorant. Now we know a lot about how to solve problems. And what is doing this is saying, I'm splitting my problem into subproblems. I want to compute the prefixes for k numbers. I split this into, I compute the prefixes for first k over 2 numbers, and for the most significant k over 2 numbers. And when I have that done, I just need to add this bias to each of them here. Then I have an element where I'm dividing, and then I'm combining the solution. Then the proper name of this approach is divide et impera et intellige. Okay? That was the way the Romans were proposing. Then you divide, and you win, but you also manage in a proper way the solution, in an intelligent way. And this is the combination of the solutions. Now, if you apply that, you get that kind of recurrence and that kind of cost, which are asymptotically very nice. I see. We don't have that much time. Okay. Now, this is another approach. And this is Brain-Kung construction. What is this doing is saying, instead of dividing in 2, I'm diminishing the dimension of my problem from k to k over 2. How do I do that? I do the addition pairwise of numbers, and then instead of having k numbers, I have k over 2 numbers. I compute now all the prefixes for those k over 2 numbers, and what I have to do is now to compute what I'm missing. Because there are, due to the reduction at the beginning, there are some terms which I don't have, and then I have to do that. This is another heuristic, and this ends up in a different kind of story. Now, let us look a bit at the Braincone network on an 8-bit adder. It is adder, but you see we don't deal with any kind of XOR. We don't compute the sum. I said we don't compute the sum because that one is kind of trivial. The carry is my problem. And I have my bits from 0 to 7, and I have all the P's and the G's for the bits. This is part of the story, otherwise I cannot do anything. I said the first step will be to simplify my solution, my problem. Then instead of having 8 bits, I will group them in pairs of 2, and my problem will have now 4 bits. Then I apply at the first level, you see I'm constructing a tree. This is what I'm essentially doing. I am applying the cent operator to neighboring bits, and then from 8 I have 4. What those guys will tell me, they will tell me something about carries and about propagation. Then this will tell me about what it's this interaction, this is this interaction, this is this interaction, and this is this interaction. They are kind of decoupled. They don't tell me the big picture, but I am building it in a kind of incremental way. Now I started with 8, now I have 4. I apply again the same trick. And then I combine those 2 and those 2. Now this will tell me about the interaction 0, 3, and this will tell me about the interaction 4, 7. Now I go one step, because remember I diminish the dimension and now I have to increase it back. And in order to increase it back, okay, I have to do that kind of things here. And then I combine this with this, and this with this. And then I am finished with this level. And now I have to return and complete what I'm missing. And that will require some 3 other cents. Then I have said, this is telling me the story 0, 1, which is good for output. These 2 will tell me the story 0, 2. These 2 will tell me the story 0, 3. These 3 will tell me the story 0, 4. These 3 will tell me 0, 5. These 4, 0, 6. And these 3, 0, 7. Then I got all the carries. Actually, there are no carries, there are P's and G's. But if I know P and G, I know the carry. For all the bit positions, then from the least significant to all the bit positions. It's a nice regular structure. All of them are computed. I only rely on that kind of simple things. And some interconnects. Some are slightly longer, some are very local. When I complete this calculation, you know, and the worst case, the longest path is 4 such operators, I have P's and G's. Now I can compute all the carries in these locations, and then I can compute the sum. Now I can apply the same thing for larger adders. And the principle is very much the same, you know. I'm taking pairs, I'm diminishing now from 16 to 8, then from 8 to 4, from 4 to 2, and then I finished the division, I got to 2, and then now I have to reconstruct whatever was missing. And if you look at the construction in a logical way, you will get that you have like 6 levels. However, those are actually overlapped because this calculation and this calculation can happen in the same time. And in this way, I can compute a Brancombe carry network for any kind of feather. The delay of this network will be logarithmic in the number of bits. It's a tree. And I can, you know, when you will get that kind of homework and maybe in the exam, what you have to look at, you have to look at the number of bits, because I might be nasty and give you 13-bit operands. Then they will not be quite well, you know. I'll certainly be nasty, right? I won't give you 16-bit operand because you can copy from the book. Okay, now, this is the Coggy-Stone structure is the same kind of thing. I'm still operating on a tree, but now the combination is different. Now, if you look at this diagram and to the previous diagram, what do you see? Both of them will give me a solution. But, you know, just from bird eye inspection, I see that this is, you know,
More wire.
okay, more wires and it's more population. Yeah, I have more cent operations. But I also have something else. I have 4 levels. This is still 16-bit. Then this one had 5 levels, and this one has 4 levels. Then this is faster. Is it really faster? And you look at me, what trick is he asking us again?
Each level is slower here.
Why would it be slower?
That's no more operations.
No, it's doing the same operation. Each bullet there, it's a cent operator. It's just the methodology, the combination technique is different. It's based on the other approach. What do you see? You see more bullets?
Yes, so
I was asking. Is that a Greek habit? Whenever you ask something, you should ask back, right?
if you don't know it,
Ah, okay.
you speculate.
That's a way out.
Yes.
Safe way out. Sure, you may ask. You wanted to say something.
You're asking if it's faster.
Mhm.
I think it might depend on the speed of the wires. You may still
Okay,
be
then
limited
you are touching the right point. In just a sec. Don't jump the queue. I know South and Eastern Europeans don't like to stay in queue. They always find creative ways to jump the queue. I'm coming from that part of Europe also. I should be able to understand. Then in normal, let's say, obsolete CMOS technology, what we cared for were the gates. The gates were the contributors to the delay. In deep submicron technology, the wires are the big contributors. And you see here, you have wires which are longer. And then even though I see 4 levels, depending on the way I'm doing the layout, this might not be faster than the previous one. See? In here, the wires are kind of shorter. And also, the long wire, it's not on the critical path. The critical path is this one. Yes?
And also the funny, you have to drive for each line, on the next one, 4 gates, like if it's basic gates. So the funny becomes, so the delay from the basic.
Then when you look at the inputs, then I will need some stronger buffers to drive the unit. But this may or may not be a problem, because this is a real register. You have your operand in a register which is assumed to be solid. Then if you have inside the network moments where you have large fan-in, then you will have to make those gates stronger. But those, you understand what I'm saying or not? Okay. Now, those are different kind of approaches, and you see delay and cost in that kind of things, and you see all of them are similar, all of them are logarithmic. Now, which one is better depends on the technology, depends on the dimension of the operand, because whenever we deal with well-behaved operands, like 16-bit, 32-bit, things are, obvious. When they have, funny dimensions, things may not be that obvious. Now, there is also a way to do hybrid stuff. Then you have the two networks, Brancombe and Cogiston. 6 levels, actually 5 levels, 26 cells, 4 levels, 49 cells. Expensive and faster, cheaper, but slightly slower. And this is an in-between solution. You combine the heuristics. Those are basically heuristics. You start with Brancombe, then you diminish the problem from k to k over 2 by combining neighbors. Then you start with 16 bits, you arrive to 8. You apply now Cogiston to 8 bits because your problem is smaller and the cost will not be that high, and eventually you can win a lot in delay. And then after you solve everything in Cogiston, then you compute the right solution for 16 bits, then you have to extend the solution back to 16 bits based on Brancombe. And you can play different kind of combinations. You can also say, no, this is not okay, let us assume I have a 64-bit addition. I apply first 2 levels of Cogiston, then I diminish from 64 to 32 to 16. Then I apply Brancombe twice, and then I go for Cogiston, and then I finish the Brancombe again with 2 levels. Then only the sky is the limit in this matter. You just have to make the right choice for your, for the dimension of the operand. No, those are a bit obsolete things. It's again about the implementation, Manchester, carry chains. No, we don't care for that. I don't have much time, but maybe I can say a couple of words about that. Then we saw linear time, ripple carry adders, simple but slow. Logarithmic time, carry look ahead, the first idea, the principle of creating a tree, propagate things in the tree back and forth, glitches, irregular. Then prefix networks. And prefix networks are, what we have and what we can, build. It's kind of the best solution today. There are other kind of tricks, however, and this also relies on propagate and generate stuff, but it's applying a different principle. And those are called carry skip adders. The idea in here is to utilize a highway whenever you have it. What do I mean by highway? If I look at the first ripple carry adder, when there is a carry, and the carry is, let's say, coming into this block, and this block is propagating, it will take me 4 hops in order to come to the output. However, I know that this bit is propagating if I'm computing the propagate for all the bits, and I can compute the OR of them. It's like I'm computing the block propagate. Now I don't care for generates. I just compute propagates. And then whenever a bit is coming here and this block is propagating, instead of rippling through the block, I'm going around the block. And this is we'll revisit this concept Monday. It's just, you know, I'm actually overusing your time, but I will finish this. This is a different way to make use of propagate kind of information. And it's logarithmic again, but as you see, I just need propagate for the block, some kind of maxes here, and standard 4-bit adders. Then from the hardware point of view, it's simpler, okay? Then I'm done for today. I'll see you on Monday.